Lesson 9.4 is optimization. Optimization means finding maximum or minimum values in given models, specifically something like maximizing volume with the smallest amount of surface area or something like that, or maximizing revenue and minimizing cost, that kind of thing, where you want the most of something while not overutilizing your resources. So in this first example, we have a cylindrical cat food can that has to have a volume of 200 centimeters cubed, and the radius of the can is r, the height is h in centimeters. So given that, explain why pi r squared is equal to 200, rearrange that equation to make h the subject, which means solve for h, and then write an expression for the total surface area of the can. Once you've done that, substitute your expression from part B for h into your expression for surface area and write an equation of the surface area in terms of just the radius. So go ahead and pause the video and try parts A through D. The reason that pi r squared h is equal to 200 is because the volume of a cylinder is pi r squared h and the volume of this specific cylindrical can is 200. So those two are equivalent to each other, given that the radius is r and the height is h. So then using this, we want to solve for h. So I just divided both sides by pi r squared, so you get that h is equal to 200 over pi r squared. Using the formula booklet, surface area of the curved surface of the can, so the outside of the can, not including the top or the bottom, is 2 pi rh. But then we also want to include the tops and the bottoms of the can. So you also have to include 2 times pi r squared. That would be 2 times the area of the top and the bottom. And then given that, we want to write an equation just in terms of radius, because it's really helpful to have just one variable for your function instead of 2. Right now we have our surface area in terms of 2 different variables, the radius and the height. But here we have the height written in terms of the radius. So we can replace the height and write the whole surface area just in terms of the radius. So I replaced h in part C with the h that we found in part B, 200 over pi r squared. And I simplified, the pi's cancel each other out, and one of the r's cancels with the r in the 2 pi r. So you end up with the surface area in terms of just the radius is 2 pi r squared plus 400 over r. Now we want to use our graphing calculator to plot this equation, so just graph it on your graphing calculator and then find the minimum surface area of the can and the value for r for which this occurs. So go ahead and pause the video and try the last part. Here's the graph of the function. I graphed it only for positive x's and positive y's because you can't have negative radius and you can't have negative surface area, so that's why I only graphed this one little part right here. And then using this, I found the minimum value, and so the minimum surface area is 189 centimeters squared, and it occurs when the radius is 3.17 centimeters. So this is important because, for example, if you're producing this and you know that you have to have a volume of 200 centimeters squared, you want to use the least amount of material in order to make this can. So if you have the radius set at 3.17 centimeters, it'll fulfill the fact that the volume has to be 200 centimeters cubed, and it'll use the minimum amount of surface area, so the minimum amount of aluminum to make the can, which will therefore minimize your cost. In this example, the revenue R of a certain product can be modeled by the function R of x equals negative 0.167x squared plus 100x, where x is the number of items sold. First, we want to plot the graph of R against x. Make sure you indicate any important features of the graph, and then find the maximum revenue and the number of items sold that maximize revenue. So go ahead and pause the video and try this one. I used my graphing calculator to plot a graph of R against x. So on the x-axis here we have the items sold, and on the y-axis we have the revenue. It didn't say, but I put it in dollars. So we had an x-intercept at 0, 0, an x-intercept at 599, 0, and then a maximum vertex here at 299, 14,970. So then the maximum revenue was 14,970, and it occurred when 299 items sold. I put this down here as well just because this would be how you would do it by hand if you weren't graphing it anyways. So x, again, the x-coordinate of your vertex is negative b over 2a when you have a quadratic, so I plugged in b is 100 and a is negative 0.167, and you end up with 299 rounded to 3 significant figures. And then to find the actual maximum revenue, you would plug that back in for x, and you would find the maximum revenue to be 14,970. So this has been optimization and maximizing and minimizing.